So in every unit that we'll do, we'll have at least one unit question. So this is a good opportunity for you to know a question ahead of time of something that will be on your test because technically you're given the question ahead of time. And this gives you an opportunity to practice a problem exactly as I want you to think through. But they're usually very critical thinking type questions. And so even though I won't give you the answer specifically, everything we've done in this chapter should prepare you to be able to answer this question. And so for this question, this molecule that you see here, and this should say on Canvas, sorry, I still kind of mix up, even though it's been many years, still mix up Canvas and Portal in terms of names because we used to only use the Portal. So sorry about that. But this particular molecule is a drug that's used for asthma. So it's specifically for it's called salmeterol. It's a long-acting bronchodilator. I talk about this when I teach medicinal chemistry. This particular drug was introduced by GlaxoSmithKline in the 1990s, and sometimes you'll see it marketed with another drug, at fluticasone, which is Advair. But it's used by people who are asthmatic. And on this particular molecule, we see primary alcohols, we see secondary alcohols, we see ethers. We do see a phenol, although I do not require you to know how to make phenols until the end of the semester. But this particular molecule, the question that you're asked is how do you install that primary alcohol, secondary alcohol, and ether? Those are things we're going to learn through the semester. So you want to practice like what kinds of reactions can do those. In addition to understanding the property of alcohols, which was in your previous video, understanding some of the things that we'll learn about alcohols might be interesting. And this is an application. So methanol, for example, is poisonous, and it's poisonous because of something we're going to learn about in this chapter, which is oxidation. So when you drink methanol or you take in methanol, the reason it's poisonous is because it undergoes oxidation, and that oxidation produces formaldehyde, and formaldehyde is extremely toxic and carcinogenic. Ethanol, on the other hand, the reason that people get alcohol poisoning if they drink too much is actually for the same reason. We can oxidize ethanol, and ethanol then produces ethanol and ethanoic acid, which is poisonous. And some other applications are propanol, 2-propanol. We've been seeing a lot lately in the last few years. It's in your rubbing alcohols, in your hand sanitizers. And then ethylene glycol, which is antifreeze. So if you live in somewhere cold, you might be using antifreeze, but your cars all have antifreeze in them. It is actually quite toxic, especially to pets and children. You have to be very careful with it. Another place that we see alcohols, and you don't have to write this, we'll talk a little bit more about these molecules at the end of the semester. But these molecules that you see here with all these alcohols, these are sugar molecules, and you can get sugar from most plants. Well, all plants have some sort of sugar molecules. And I don't mean like table sugar. Like table sugar is a type of sugar molecule in the class of molecules called carbohydrates. And a green application is using these plant molecules to then make ethanol. And ethanol, one application of it is people use it and for some cars as part of the fuel. Now, there are some ethical issues with this because one idea is that if we can produce enough corn, we can feed a population of people. But on the other hand, people use it as fuels rather than finding greener ways of powering our vehicles. We're utilizing food to do this. And so the government does subsidize this, which is something that, is a little bit of an ethical dilemma. So the last thing before we talk about some mechanisms, so the major thing that we'll talk about is using strong bases to deprotonate alcohol. So in your textbook, they talk about using you can use strong bases like alkyl halides or lithium halides to deprotonate alcohol. So that's just an acid-base reaction you saw in organic 1. But you could potentially also use sodium metal, potassium metal, lithium metal, any of your group 1 metals, and make your alcohols become alkoxide ions. So basically they take off the hydrogen. Now you don't need to be able to draw that mechanism. It's a redox type mechanism, but just know what happens. So you can find that reaction in your textbook as well as your mechanism handout. So make sure you take a note of that. So our first mechanism that we'll talk about is a reduction reaction. So we're going to specifically talk about the reduction part of the redox, where you can take a carbonyl and turn it.
Let's do the generic acyl nucleophilic substitution. And basically how that works is acyl means carbonyl. You're going to add a nucleophile to it. And we'll also talk about acyl nucleophilic addition. And that's actually the one we're going to start with first. Next time we'll do the substitution one. So this would be a replacement of a leaving group. So it's like a substitution. This would be adding to the carbonyl. So let's go ahead and draw. We're going to start with this mechanism and then we'll do the substitution next. It's virtually similar mechanisms except adding a substitution part. So when we did an addition in organic 1, we added groups across the double bond. So we're going to basically do that. So the generic mechanism is you take your carbonyl with whatever groups are on your carbonyl, whether they're carbons or instead of carbons, we could have had hydrogens. So we're talking about ketones or aldehydes specifically for the addition. The other carbonyls we'll focus on for substitution. So you take your nucleophile, and typically it's a strong nucleophile, but some weak ones can work in certain conditions. It attacks the carbonyl because the carbonyl is partially positive because of the oxygen. So you're going to attack the carbonyl carbon, open the pi bond, and give that oxygen an extra electron, which will make it form an alkoxide ion. So this is called an alkoxide when you have that negatively charged oxygen. And you added your nucleophile. Now, this is not terribly stable, so the last step that typically happens is that we protonate. Usually the best thing to do is protonate with an acid, so we use H3O+, but your textbook talks about using water or alcohols. Those work. They're just going to be very slow because that equilibrium is not going to be terribly fast. And again, you can review these mechanisms in the mechanism videos that are posted. We're going to go back to this mechanism, but this time we're going to use a hydrogen nucleophile, and most commonly we use sodium borohydride or lithium aluminum hydride. Lithium aluminum hydride is extremely reactive, so typically we don't use it unless we have to, and with aldehydes and ketones we don't have to. It's way too strong. It's actually quite dangerous to use, so we usually use something milder. We'll talk about when we might need to use something stronger. So we take sodium borohydride. Remember, boron is more electropositive than hydrogen, so the hydrogens are actually more negative, and there's no lone pairs on the hydrogen, so the electrons come from the bond, attack the carbonyl, open the pi bond up, just like we did before. So if you look, same mechanism, except we're using hydrogen. We're using the hydrogen as the nucleophile. That's why we call it a hydride. And so this is sodium borohydride. We open the pi bond up, and we've added that extra hydrogen. And so because we've added the extra hydrogen, we now have made that alkoxide ion, and we can protonate with an acid. So that would be step number 2 in the mechanism. So if I were to write this out, And again, you can use aldehydes as well. Number 1 would be the sodium borohydride. The sodium is just a spectator. Step number 2 would be your acid. So you could also use water and another alcohol. However, those are going to be typically very, very slow, so we generally don't use them. Now remember, we don't have to draw in that extra hydrogen because it's understood, but just for the sake of understanding, we're going to draw it. I'm also going to summarize what kinds of products you get depending on what those R groups or whether hydrogens, but it's the mechanism doesn't change. What happens when we have carbons as a nucleophile? So we don't often see carbon as a nucleophile because carbon is typically more electropositive than the most things. But just like the hydrogen, if you put the carbon on a metal, that metal is going to be more electropositive. So a very common example is if we put our carbon group attached to a metal like lithium, or we put it on a magnesium, and other metals. So there's actually a whole chapter on that I want you to read. But with magnesium, because magnesium needs 2 groups, we can put an X group, which is going to be like a halide or a tosylate or a mesylate or a triflate. Those all work on here. And this is very reactive. The problem with using lithium is it's actually so reactive that typically it's too reactive for most of the things that we're going to do. So something mild that works with aldehydes and ketones is, or it's not mild, but it's milder, is what we call the Grignard reagents. So Grignard reagents were developed by Dr. Grignard. And in this mechanism, you take your carbon group, and I'm going to put 3 here to represent it's a different compound. I'm going to do 1, 2. So these could all be 3 different things, or they could all be the same. And we react. Again, carbon has no lone pairs in this case, so the electrons are going to come from the bond, open the pi bond up, and we're going to be breaking the bond between the magnesium and the carbon group, just like we did between the hydride and the boron in the previous example. We again get our alkoxide ion, but this time we're adding another carbon group. And again, all 3 of these carbons could be the same, they could be different, so you could get all sorts of variations of products. And then our last step is protonation. And again, the video for this you can review as many times as you want to review this mechanism. But it doesn't matter what the carbon group, what the nucleophile is, the mechanism is always the same for these types of molecules. So we gain that, we gain our carbon group. So the difference between this and the hydride is now you're gaining carbon groups. So quick little overview. If I'm adding the hydride, as in sodium borohydride, you can also do the same mechanism with lithium aluminum hydride. It's just way too reactive, so we typically don't use it. If you start with formaldehyde, which has no carbon groups on there, essentially you're adding hydrogen across the double bond. On the carbonyl side, it's a hydride. On the oxygen side, it's a hydrogen from an acid. So if you just imagine breaking the double bond and then adding a hydrogen and then adding a hydrogen. And remember, we don't need to always draw the hydrogens. So in this case, you get this, which is methanol. There's no other options in this case. If we started with a different aldehyde that only has 1 hydrogen on there, we would do the same thing, break the carbonyl, add your hydrogen, and then add your other hydrogen. So I'm going to put a star here representing what we're adding. If I had a ketone, And if you hear my dog snoring, I'm sorry. You can then break that carbonyl. So the same would be true if you were to do the Grignard. If you start with formaldehyde, we're adding a carbon group to the carbonyl carbon, but we're adding a hydrogen group. So it would be the same thing, but wherever you see the asterisk that I added, instead, you would be adding carbon groups. So if I added my Grignard, the only difference is I've just changed the nucleophile. So no matter what I do in the case of a Grignard, all I'm doing is adding a carbon. So I'm adding a carbon, adding a carbon, adding a carbon, not one carbon, but whatever the carbon group is that I'm adding. So where you see the R groups. So it's the same mechanism, basically just adding a nucleophile. And so when you practice this, you will start to be able to like rationalize where things are going even without drawing the mechanism, because you'll kind of get the gist. But this is the generic mechanism. So I mentioned the acyl substitutions. These are when you have carboxylic acid derivatives, meaning that you have some sort of leaving group here. And the idea is when you do this mechanism, it's a substitution because you're going to replace the leaving group with that nucleophile. And the identity of the nucleophile might cause you to end up doing a second reaction, which would be the addition. So this would be the substitution. And depending on what kind of nucleophile, you might get an addition as well. Now, the types of nucleophiles that would give you that addition would be strong nucleophiles, very strong nucleophiles. So for example, lithium aluminum hydride and Grignards can do that. So let me draw you an example of a strong nucleophile that can do this. And in the next, in a couple of chapters, we'll talk about more examples. This is just the beginning. So for example, if I had an ester and I took a Grignard, I'm going to put a little asterisk here. I can attack the carbonyl, open the pi bond up. And this OR group is a leaving group. It's not a fantastic leaving group, but it's a decent leaving group. It's the only thing that could potentially leave. In the other examples, I had no leaving group in the additions, so nothing could leave. So while you're waiting for your solution to get protonated, this step happens faster than you can protonate. And because of that, the alkoxide comes down and kicks the leaving group out. So this is the substitution. So you may not think of it as a substitution, but essentially we're using that oxygen to kick out a leaving group. So it is like a SN2 type mechanism. And in our case, we reformed that carbonyl. And in this case, I've formed a ketone. But remember, ketones can undergo Grignard reactions, so this can happen again. Now, some nucleophiles are not strong enough to do this 2 times like this, but Grignards are. And we'll spend more time in another chapter talking about the ones that are not so strong. So we I forgot to put my little asterisk back. I'm going to put 2 asterisks to represent that I added the second one. Now there's no leaving groups available, so the only thing you can do is sit back and just protonate. So we'll just wait until the protonation step happens. So for these carboxylic acid derivatives, you added the R group twice. So we'll come back and do a review of that again. For the hydrides, now sodium borohydride, like I said, it's strongish, but it's not that strong. So it turns out sodium borohydride